All right, we are now recording, and the slide doesn't look like it's very healthy, does it? This is Chapter 9, Infinite Series, the last section in that. Oh, but this looks better. 9.10 is Taylor and Maclaurin series. Okay, any other questions before we get going? Was it honors college stuff? Or yeah, I figured it must be. So I don't know. Dr. Thomas, I know, is on Birmingham campus today. She's here, there Monday, Wednesday, and Friday, and she's here Tuesday, Thursday, and sometimes Friday. But, okay. All right. The objectives in this, we're not going to be doing all this. Find the Taylor or Maclaurin series for a function, find the binomial series, and use the basic test for the Taylor series to find other Taylor series. And I think, hopefully, what you'll see, Taylor series are one of the most powerful tools that we have in mathematics, okay? And with that, once upon a time I had a pen here. There it is. Fred is here. All right, good deal. So, just a slideshow on Taylor series and Maclaurin series. We will study at least go over a general procedure for deriving the power series for a function that has derivatives of all orders. That's a requirement. The next theorem gives the form that every convergent power series must take. Okay? If f is represented by a power series, f of x is equal to some summation of some a sub n times x minus c raised to the n power. Okay, now what they didn't put here, what the counter was, n going from 1 to infinity, okay? Or maybe some other number, okay? So it would be a sub 1 times x minus c to the, I think actually it starts with 0. A sub 0 times x minus c to the 0, so it's just a sub 0, okay? Then a sub 1 times x minus c to the first, it's a sub 2 times x minus c to the second. So in other words, your power series for x minus c, okay? So if this f is represented by that power series for all x's in an open interval I containing this number c, okay? Some interval containing the number c. Then this a sub n that we're talking about is the nth derivative of f. F is the power series. Nth derivative of f evaluated at c, okay, in the interval, divided by n factorial. Now, when I said n can be 0, what is 0 factorial? Anyone know? No, that's the thing. This is one strange thing about factorial. 0 factorial is defined to be 1. Okay? 1 factorial is also 1. 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and on and on. But 0 factorial. So that's why you can have a sub n could start with 0, because the 0th derivative is the function itself. Okay? Then after that, first derivative, second derivative, and then you divide by that. And f of x is equal to f of c. That's your first one, because 1 over 0 factorial is 1. So that's your coefficient, is 1, times f of c, plus f prime of x minus c to the first power, because 1 factorial is also 1, okay, plus 1 over 2 factorial, which is 1/2, f second derivative of f at c times x minus c squared, and so on and so on. Up to the nth one would be the nth derivative of f. That's why it has to be, f is represented by power series, they say up here, for a function that has derivatives of all orders, okay? And see, a polynomial wouldn't be very good here. You don't need it. It's already a polynomial function. But because if it's a third degree polynomial, you don't have derivatives up to, but to 3, After that, they're all zeros. Speaking of, I didn't say that, okay. Ryan's here. Okay. So that's the form of a convergent power series. Okay? And I'll tell you right now, what makes it convergent pretty much is the fact that these factorials, these are getting to be huge numbers, so basically you can almost, just based on that alone, say that they converge. The coefficients of the power series in that theorem are precisely the coefficients of your Taylor polynomials that we did back in whatever, 9, 8, or 7, whenever we did Taylor polynomials for f at c. For this reason, the series is called the Taylor series. There are Taylor polynomials back there, Taylor series here, when you're adding them all together. Okay? Okay? Here's the definition of the Taylor and the Maclaurin series. If a function f has derivatives of all orders, okay, that at x equals c, then the series, the summation n equals 0 to infinity of f sub n at c divided by n factorial times x minus c to the nth power, and that's equal to f of c plus f prime of c times x minus c plus, you keep going up, f double prime over 2 factorial, and so on and so on, up to f, the nth derivative of f at c divided by n factorial times x minus c to the nth power, and Devin Todd is here. Speaking of power, okay, okay. Now, and they keep on going. This is called the Taylor series for f at c. Now, if that c happens to be the number 0, okay, if that c is 0, now we're not centering the function, or you know, have to center it, but having it around some number c. That interval, remember, had to contain c. Now, that interval could have been huge, it could have been small, had to contain c. But if that c is 0, meaning you have to be right at the origin, or fairly close to the origin, then the series is called the Maclaurin series of that. Okay? Only difference in the Taylor series and the Maclaurin series, Taylor series is any number c, any real number c. If c is 0, though, it's called the Maclaurin series. They have a little blurb here about Colin Maclaurin, who was pretty sure he was Scottish by that name, but let me see. They don't even mention that here. The development of these power series to represent functions is credited to the combined work of many 17th and 18th century mathematicians. Gregory, can't even recall exactly who he was. Newton, I think I know who he was. John and James Bernoulli, they were the Bernoulli brothers. Leibniz, Euler, Lagrange, Wallis, Fourier all contributed to the work. However, the two names that are most commonly associated with the power series are Brooke Taylor, who we talked about in an earlier section, and Colin Maclaurin. Okay. Now, let me, while I'm thinking of that, jump onto that issue. This, of course, my best class ever. I've had how many? One research paper turned in, okay, out of 9 students. And we're on the last week of class. That means this is it, folks. Wednesday is the last day to turn it in before you start losing points. So I hope that everybody would have used that long week that you had to get your papers done, but they haven't been flooding me this morning. So please, folks, get your papers in. Also, my best class ever, the first test, I've already received 5 out of 9 of those in. 4 people haven't even turned in the first test. Okay? Second test, I got the first one in this morning. Okay? So that means there's at least 4 of you that I don't even have a grade for on the last week of the class, okay? any grade. Research paper, first test, second test, okay? And the rest of you've turned in test 1. You're leading the way, folks, but test 2 still isn't in yet. And I'll be giving you test 3 on Wednesday. That's your final exam. So please, folks, get the stuff in. A paper and a test this week, not good time management, I would say. Okay, so try to get them in. Okay, so enough of the paid political announcement. All right, so that's what your Taylor and Maclaurin series are. I say 2 of the most powerful infinite series you'll ever run into in mathematics. Okay, we're not going to do this, but I was going to point it out. You might say, what functions have infinite number of derivatives? Well, quite a few. Your sine, your cosine, they certainly do. Now, problem with tangents and the other trig functions, they all have discontinuities. So you have to really restrict your intervals that you're going to be trying to do those. They do have infinite derivatives, and they get really messy. Sines and cosine, they just back and forth between sine and cosine, and plus and minus signs too, but other than that, they're pretty easy to do. Your exponential functions, infinite number. Log functions, infinite number of derivatives. Any function a power function where your n is not an integer, okay? If it's to the 1/2 power, infinite number of derivatives. To the -2 power, -1 power, infinite number of. So there are quite a few functions that do have infinite number of derivatives, okay? That are all defined, so deal with that. Now, of course, n to the -1, that also has some problems with discontinuities as long as you stay away from those. Sines and cosines, exponentials, no problems anywhere. Those are good everywhere. Okay, so we're not going to do this, but that is an example of a function that would be, and this would be a Maclaurin series because it's evaluated at 0. And yeah, not going. Well, let's watch them do it. If f of x is sine x, this is a general form. If f of x is sine x, then this would be sine at 0, which is 0. This is cosine at 0, which is 1. This is sine at negative sine at 0, which is still 0. This is negative cosine at, so this is then a minus this. So this, you skip the even terms, and you have only the odd terms here, odd derivatives, and they alternate signs. This is positive, that is negative, next one positive, negative. Okay. So that's what you get, because f of 0 is 0, and anytime you have sine, which is every other derivative is going to be a sine, plus or a minus. Okay? F prime of sine is cosine. Cosine of 0 is 1. So your every other coefficient, or at least the prime coefficient, is 1, plus or minus, and they alternate. F double prime is minus sine, that's 0 again, and f to the third derivative of f is minus cosine, which is then is a minus 1. So from then on, you just keep going. The even derivatives are all 0, the odd derivatives are plus 1, minus 1, plus 1, minus 1 for these. Okay, so that's a 0 again, and plus 1, and so on and so on. The pattern repeats itself after the third derivative. Okay. So your power series is, this is a 0, that's a 0, and those are zeros. So this is just x minus, 1 over 3 factorial, which is 1/6 of x cubed, plus 1 over 5 factorial x to the 5th, and so on, and then minus 1 over 7 factorial x to the 7th. It basically boils down to this. Only the odd powers of x, 1, 3, 5, 7, 9, alternate signs, plus, minus, plus, minus, plus, minus, and your denominators are whatever your exponent is, your 3 factorial, 5 factorial, 7 factorial, and so on. And believe it or not, that gives you the sine function. Okay? And guess what? When you punch in your calculator, oh, and by the way, this is x is always in radians. Don't ever try this with degrees. It won't give you the right answer. X is in radians. They never mention that, but they're sort of assuming that. And if you want to know how in the world you calculated when you put sine of 0.7 in, and it gave you an answer, it did this. It's doing a Maclaurin series, okay? It's just doing it really quickly because they don't store that in the memory of the calculator. You couldn't store everything. It's doing a Maclaurin series, okay? And this is a more complicated way to write it. Why not leave it the way it was? But anyway, by the ratio test, you can conclude that this series converges for all x. We talked about the ratio test. You don't have to do it, but it does converge. Okay? Because anytime you have a polynomial, a power series in the numerator and a factorial in the denominator, factorial wins. It overweighs that every time. Okay, you cannot conclude the power series converges to sine x for all x. You can simply conclude that the power series converges to some function, but you're not sure what the function is. Now, this is getting a little bizarre here. This is a subtle but important point in dealing with Taylor and Maclaurin series. To persuade yourself that that might converge to a function other than f, remember that the derivatives are being evaluated at a single point. In this case, c, the way they've written it here, earlier we did it 0. Okay? It can very easily happen that another function will agree with the value of f prime of x when x equals c and disagree at other x values. And of course, this is a bizarre function. It's a piecewise defined function, which makes it bizarre, but it is bizarre. It's 1 everywhere from negative infinity up to negative pi has, negative 1 from negative infinity to negative pi has. And then it's a sine function here. Well, that's what you're evaluating, near x equals 0. So that's going to give you the right answer everywhere. It just won't give you the right answer out here because it's no longer sine out there. So you really almost have to concoct functions like this that makes it bizarre like this. And this is true for all the absolute values of x between minus pi has and pi has, and then it's 1 from there on. Sure, that's a function. Is it a function you would ever use? I can't imagine it, but it is a function. It's a legitimate function. So you can't say that's a function everywhere. You can say it's the sine function and this function anywhere near 0. In other words, within pi halves of 0. Okay. You know that the series converges for all x, yet it obviously cannot converge to both f of x and sine x, where f of x is the other strange function. Let f have derivative, blah, blah. And I don't think I even want to mess with that anymore, because who would leave that alone? Nevertheless, the theorem 919 tells us that for each n, and here's Taylor's theorem, by the way. If the function f is differentiable through order n plus 1 on some interval I containing c, this is Taylor's theorem, so you can contain it around c, then for each x in I, in that interval that contains c, there exists a z in between x and c such that if you do everything up to the nth derivative, okay, it has them through n plus 1, and then this is a remainder. That remainder is the nth derivative evaluated at z, where z is some number between x and c, anywhere in the interval, whatever x you get. If c's here and your x's are somewhere on either side, then pick a z that's in between the x and the c, and there is some value there. That will give you exactly what the rest are. That's your remainder. the fact that your error of using that abbreviated function only going up to the nth derivative rather than the infinite series, if you are satisfied that your difference will be no more than this, you're happy. And that's also what your calculator does. Your calculator only has in its memory, touch in 1/3 or something like that. See how many digits you got there. I'm guessing about 9 or so. I can almost guarantee you your calculator is only going to be good for maybe up to 11 digits. You won't see the next 2 digits, but it will be good for about 2 more digits than what is listed there. So when your calculator is doing these series, and it's a program in there, when it gets up to that this error here, okay, is no more than, is less than, if you got to 10 digits, 10 to the minus 10, then it's going to stop because it can't even display that 10th digit. It tells you you're good through those 9 digits and it's going to stop. Okay, otherwise it would just be computing forever. So that's basically why this is an important theorem. Whereas they didn't even have calculators back when Taylor came up with it, but this allows your computer, calculator, whatever, to know where to stop. Okay. Note that this remainder formula, the particular value of z that makes the remainder formula true, depends on the value of x and n. And if r sub n is approaching 0, which hopefully it is, then the next theorem tells us that this Taylor series for f actually converges to f of x for all x in that interval I. So basically this is saying if this r sub n that we talked about in the last slide, that the f of x is converging to that nth, the partial sum, well, yeah, then it's saying the Taylor series will converge to that function f of x. Sine, cosine, whatever it is. And you don't make up all these other strange things there. So this is getting into sort of nebulous stuff, so let's not spend too much time with it. Show that Maclaurin series converges to that for all x's. You just need to show that's true for all x. Now, we won't even mess with this. I mean, it's a pretty straightforward thing to do, but it gets pretty heady, so let's move on. For the discussion regarding the relative rates of convergence of exponential factorial sequences follows from a fixed x. Okay, this is what I was saying before. If you got a power series, even an absolute power series, divided by an exponential series factorial thing is going to win. Okay, it's always going to win over a power because you can just take it so far out and then the factorials keep getting bigger. The x's do not. And then squeeze theorem helps you solve example 2. Okay. This visually illustrates the convergence of Maclaurin series of sine x by comparing the graphs of Maclaurin series P1, P3, P5, P7 with the graphs of the polynomial increases so it's graphed more closely. So P1 is just x. Well, that's pretty good for x near 0. That's a very good approximation. It just falls apart there. But then when you put that second term in, you have a cubic function that does this, and now it's good even further. Okay? Then the next one's going to be a quintic function, and that's going to have 2 dips in it. Boy, look at now. You're going out to here. And then the 7th, I'm surprised that you have some cancellation going on there. and it does this number, okay? And that's good. It looks like they're at least there. So every time we're getting a little bit further and further out, and if you let this go to infinity, yeah, it's going to be good for as far as you want to go, okay? Even though the x equals 0, you're centered at 0. So yeah, the Maclaurin series does converge. You just have to keep going quite a ways out there to get it. So here are the guidelines for finding a Taylor series. Hang on to these if you ever need them. You're not going to be tested on it. We need to move on. Now, the binomial series. It's pretty interesting they put it here. I've always heard the one that's responsible for this one. Before presenting the basic list of elementary functions, you'll need to develop one more series for a function of the form f of x is equal to 1 plus x to the kth power. That produces the binomial series. Okay. Find the Maclaurin series for that f. Okay. 1 plus x to the kth power. Determine its radius of convergence. Now, you're not responsible for this. I'll just show you how they do it. Assume k is not I'm sorry. It's neither a positive integer nor 0. Okay? Because if k was 0, this is a constant function 1. Okay? F of x equal 1. That's not very interesting. If it's a positive integer, then the derivatives are going to end and become all zeros. So you can approximate it exactly with a, if it's anything other, and that's what I was saying before, if it's a negative number or a rational number, you can use Maclaurin series or Taylor series on that. So by successive differentiation, you have f of x is just given as that, so f of 0 is 1. F prime of x would be this, so f prime at 0 would be k, because this would be 1, raised to that power would be 1, that's k, okay? F double prime would be k times k plus 1 times this, to the k minus 2, and f at 0. I didn't want to do this, but I'm going to have to, I think. Sorry. My cold is much better. You probably can't tell, but it's, I guess all this talking is messing me up here. So this would be, at 0, this would be 1. So this last term is just 1. 1 to the any power is going to be 1. And that would be k times k minus 1. And you can, I think, figure out what the next is going to be. K times k minus 1 times k minus 2. K times k minus 1 times k minus 2 times k minus 3. It just keeps on going like that at 0. Okay? K times k minus 1 times ... k minus n plus 1. Okay? Now, that was the derivative part. Remember, you have your factorial underneath, okay? And here it's 1, there it's 1, here it's 2, then it's 6, then it's 24, then it's 120, keeps going, it's in factorial, okay? Again, you wind up with this is just a finite number. It could be a pretty big number, sure, but then it's a finite number, and then this is x to the n over n factorial always converges. Always converges. Okay? By the ratio test, you conclude that the radius of convergence is r is equal to 1. Okay? We didn't do the ratio test, but you can go back and review that if you want to. So the series converges to some function on the interval from -1 to 1. If you get outside there, No, it's not going to converge, because then you've got your coefficient is getting bigger too, and so is your exponential is getting quite big, and you can't guarantee they're going to overpower they won't be overpowered. You can't say they'll be overpowered by the factorial anymore. So here is the basic list, okay? Power series from some of the elementary functions. 1 over x is 1 minus x minus 1 plus x minus 1. Notice you have alternating derivatives here, which you would have because your exponents are alternating signs, okay? The first one would be a negative, then negative times negative is positive, and negative times positive is negative. So alternating signs, and then you just have a power series, okay? That interval of convergence will be 1 again, but it's centered at x equal 1, okay? This one is the one I think we were just looking at. Again, alternating signs because you have a negative derivative down here. If you think about that as 1 plus x to the minus 1, that's where you're starting. So it's going to be alternating sign, and then it will be x squared, x cubed. So that interval of convergence is also 1. The radius is 1, centered at 0 then. Here's your log function. Now, of course, x can never be 0. You can't take the log of 0. X can never be negative. You can't take the log of a negative number. So therefore, your log function is also, comes up, and notice here, plus, minus, alternating signs again, and x minus 1 to the first, second, third, fourth, fifth, and so on. That interval of convergence is also 1, but it's centered at 1. Of course, it can't be 0. Okay. Each of the x everywhere is good. And this is it, by the way. 1 plus x squared. Notice all these are pluses, because see that x is always positive, okay? And all its derivatives are positive. This is over 0 factorial, over 1 factorial, 2 factorial, so that converges everywhere. No question about it. Sine converges everywhere. Okay? Cosine converges everywhere. And notice the sine is the odd powers, alternating signs. Cosine is the even powers, alternating signs. Okay? Now, arctangent you can do, why you ever want to, I don't know, but it's only good for a certain radius, between minus 1 and 1. If you think about it, it's the only place where arctangent is defined. Arctangent starts here and it goes there, and it's only defined for, well, that's not quite true. That's the values of it. Okay. Arcsine you can also do that way. And then here's your power series in general, the one we just did. And the convergent x equal plus or minus 1 for this last one depends on what k is. So we'll leave that alone for now. Here's another power series. Oh boy. How do you do this one? Well, your cosine, you know what it is, but then what you have in the numerator of that is powers of the square root of x, because this is cosine x. I wish they'd used a different letter here. If they say cosine u, but then let u equal square root of x, this would have made a little more sense. I just hate they did that. It's just, I think, sloppiness. So you just take the square root of it everywhere and look at what you wind up with. Your denominators stay the same, but your numerators get divided in two, basically. And so there's your power series for f of x. That series converges for all x in the domain of that That is, for all x is greater than 0. Can't be anything less because that's not even defined. This thing right here is not defined for that. Even though there doesn't seem to be anything wrong there, you can't do it. You have to stay in the all right. Ooh, way more than what we have time to go over. I wish I hadn't taken this much time on it. There are some review questions, exercises at the end of the chapter 9. 1 or 3, and these are all at Calc Chat. There's no Calc View. 1 or 3, if you need more to practice on that, you could do those. 5 or 7, you could do those. 9, you could do those. 11 through 17, you could do those. 19 or 21, those. 23, that one. And then there's an application 25, which I don't think we did. But we must have. So you try 25 if you like. 27, all are at Calc Chat, by the way. Partial sums, that one. I think 29, and you could probably do 31 or 33. I'm sorry, I forgot to bring my glasses today. I'm having a hard time seeing. And then we did one like 35. You can certainly do that. And 37 or 39. 41 is one you could do. Stop there. I don't think we did the integral test. I know we went over it, but I believe that's from a later section. So those are just some more problems if you wanted to do those. Okay. Let's move on to chapter 10. Sorry, that took longer than I wanted it to. All right. I hate to do this too, but I think I will. Because you will need this in Cal 3, just a little bit of it, not much. But let me familiarize you with you here. It's not required in this course, but since you will need at least a little knowledge of it, let me do this here. Chapter 10 is conics, parametric equations, and polar coordinates. Okay? The course description said we do parametric equations and polar coordinates. Didn't say anything about conics, but because it is such a common term, a common concept, let's just go a slideshow of it. Conics and calculus. Just to understand the definition of a conic section, analyze and write equations for parabolas, ellipses, hyperbolas. You'll see why. Cal 3 starts with surface, oh, that's not what I'm wanting to say. Goodness, it's cold. Surfaces depend on these, so you do need to know. So let's just look at what a conic section is. First, conic means from a cone, okay? The intersection of a plane and a double-napped cone. Now, you may have thought a cone was just this, because that's what you use in chemistry or something like that, right? Well, a cone is always has its mirror image. So this is called a double-napped cone. Now, and sort of by definition, a cone makes a circle, okay? For a plane, okay, so a conic section is described as the intersection of a plane, some plane, with a double-napped cone. Notice in figure 10.1 that the four basic, oh, good, here's Jemiah.
Also, the last day to turn in the paper without it being late.
Say this one more time.
The last day to turn in the paper is like Wednesday, like late.
Yeah, after Wednesday it will be late. Okay, so last day to turn in the paper without losing points is day after tomorrow, Wednesday. I've been harping on this all term. Okay. Yeah, you're absolutely right. So if this is your cone, then it depends on where the plane comes from. Double knob cone doesn't change where it's plane from. Okay? There are 4 basic conics. If the plane is perpendicular to the axis of the cone, then you always intersect in circles. Wherever you are, there's going to be a circle, except right there, it's going to be a single point. But every place else is going to be a circle. So a circle is a conic section. Now, I wish they'd have gone next to this one. What if you tilt that plane just a little bit? Okay? Then what you get is an ellipse. You can tilt it up here, you get an ellipse. Down here, wherever you tilt just a little bit, you get an ellipse. But if you have that plane just cutting through one of the cones with, well, these are just cutting through 1 and 2, but just the plane doesn't this plane goes all the way through the cone. This just covers a slice of it, and if it just doesn't ever intersect the other end of it when it just slices it, that forms a parabola. Okay? But if it's a plane that's parallel to the axis of the cone, slicing just part of it, then that forms a hyperbola. Hyperbola always has 2 opposing sides of them. They kind of look like parabola, but they're not. Okay? This is a parabola. This is not a parabola. It looks similar to it, but it's not. This always has 2 pieces opposing, and that's a parabola. That's mostly what you need to know about your conic sections. Okay? Now, when the plane intersects through the vertex, and you get just a single point, when it slices through the vertex, but then slices, you get a single line. If you happen to do it in a way that it slices through both, you cut that cone exactly in half, then you get 2 intersecting lines. These are both called degenerative cones, degenerate cones. There's something wrong with their, no, never mind. Okay. They're degenerates. Okay. There are several ways to study conics. You could begin as the Greeks did by defining the conics in terms of intersections of planes and cones, which we just did, or you could define them algebraically in terms of general second-degree equations. Okay? Your general second-degree equation would be ax squared plus bx plus ax squared plus bxy plus cy squared plus dx plus ey plus f. I'm sorry. Okay? Now that's the most general expression of a second-order equation, second-degree equation. You have your variables to the second power. You have the product of the 2 variables, the sum being power 2, can't exceed power 2. Then you have your linear terms, and then you have a constant term. That's the most general. Okay? The third approach, in which each of the conics is defined as a locus or a collection of points satisfying a certain geometric property, they say it works best. However, when we do, now I remember the term, quadric surfaces, that's what I was trying to think of before. We'll go back to this term, but we'll think of them in terms of all 3. For example, a circle can be defined as a collection of all the points x, y that are equidistant from some fixed point hk. That locus definition easily produces x minus h squared plus y minus k squared equal r squared. That's the standard equation for a circle centered at hk. If it's centered at the origin, it's just x squared plus y squared is equal to r squared. Okay? But if it's any other place, x minus h squared plus y minus k squared is equal to r squared. Now, I like to take it one step further, and we will be doing this later. If you divide every term, let me get my pen set up. I apologize again. I forgot to bring my glasses this morning, so kind of not hitting the squares well. Divide everything by r squared. This would then be a 1, okay? And that would be one way of expressing, or another would be x minus h over r squared plus y minus k over r squared equal 1. There's another way of expressing it. There's several ways to express that circle. We usually think of it this way because we think x squared plus y squared equal r squared. That's how we've used to say it. Later we'll see there is an advantage to thinking of it this way too. But not yet. Okay? Parabolas. A parabola is a set of points x, y, whether you've ever thought of them this way, that are equidistant from some fixed line called the directrix, okay? And a fixed point called the focus that is not on that line, not on the directrix, okay? The midpoint between the focus and the directrix is called the vertex, okay? And the line passing through the focus and the vertex is the axis of the parabola, okay? Note that the parabola is symmetric with respect to its axis. So it's equal distance from the focus and the directrix. The parabola is always going to be in between the two of those, okay? That's why the focus can't be on the directrix. It has to be separate. Okay, now the closer they are together, the flatter that parabola is. The further they are apart, the steeper that parabola is. Okay? But you'll notice here, of course, the midpoint between is the vertex, so the same distance here and here, P. Okay? And that is an important distance too. Any other distance for any other point, D1, D1, D2, D2, always same distance here to there. Okay? Always. And that gives you a parabola. Now, that's your geometric definition, well, illustration of it. Let me give you an interesting feature of this. Any line coming out of the focus, if it's reflected here, is going to produce a parallel beam. Okay? Now, you might say, so, well, you use parabola all the time. Has anyone ever used a flashlight? Yeah. If you ever notice that silver mirror that's behind the bulb, that gives you almost a beam coming out. Why? That silver mirror is in the shape of a parabola. It's not a semicircle. You may have thought that. It's not. Or a hemisphere. It's not. It's a it's a paraboloid. Okay? It's the surface of a parabola. We'll get to that next thing. Okay? Where do you put the light bulb? You put it on the focus. Okay? Now, is it a perfect parallel beam? No, it isn't, because the bulb is not a fixed point. The bulb has some dimension to it. So you get some fuzziness there, but basically your light is in a beam. Okay? Any of you ever driven a car? At night? Turned on the light, same thing. That's a paraboloid. That's a parabolic mirror that's behind that bulb, and it's sitting right on its focus, giving you close to a parallel beam of light coming out. On the receiving end of this, have you ever had a disc of any nature that you might have watching TV with or other things? Direct TV, dish TV, any of those? Guess what? Parabolic. What do you have sitting right up here? That's your receiver. Okay? That parabolic shape there, because something coming as far away as a satellite, those beams are coming very close to parallel. Okay? Coming very close to parallel. fix that toward the satellite. Satellite has to be geosynchronous orbit, always above the same point of the Earth. Fix the parabola there, have your receiver there. All those beams coming in get reflected to the focus. Because just like everything coming off the focus goes parallel, everything coming in parallel is reflected to the focus. So all those discs, and go to a TV or radio station, you see dish all over the place because they're receiving signals from various sources and sending them out. So yeah, you've used these all the time. I'm sorry, I'm spending way too long. So here's the standard equation for a parabola. Standard form for the equation of a parabola with the vertex hk and the directrix y is equal to k minus p. Remember, the vertex is the point down here, hk. H is the distance on the x-axis. Who cares about that? The k is how far it is from the y-axis. So then, and that distance we know to be p, and then k minus p would put it down on the lower side. Y is equal to, the directrix is that y is equal to k minus p. The vertex, k minus p. Also, focus is up there at plus p, so k minus p will be where the directrix is. Y is equal to that. So x minus h squared is equal to 4p times y minus k. I'll let you play around with that and see why that comes out to be true, but it is. For the directrix, x is equal to h minus p. The equation then becomes y minus k squared. Oh, this is the one opening like this. This is the one opening like this. Okay, so you just flipped around who the independent and dependent variable are. Just flipped everything around. H minus k and y minus x minus h and y minus k. Just flip places. The focus lies on the axis p units, directed distance from the vertex, and the coordinates of the focus are at h, k plus p, and h plus p, k. One for this, one for that. Okay. All right. We're not going to do the example, but I'll let you see how they did it. You've got your books. You can see that. Remember our good old completing the square? Your favorite way of solving a quadratic equation? No, it wasn't. You want to use anything but that, you're still using completing the square. Okay? Write the original equation, complete the square, blah, blah, blah. Well, first, get rid of the denominators, okay? Then complete the square. And it shows you exactly how to do all this. And that gets you your form. Your standard form for the parabola. That gives you h equal, I'm not going to go back and do all that, but that's how you go about doing this. Now, goes through the whole shebang. We're not doing this, and we sure aren't going to get into these things. So goodness, wow. The focal chord, the lattice rectum, that doesn't even sound good, does it? Okay, reflector, okay. I'm not even going to mess with those, okay? Oh, here's what I was showing. Maybe I should have done it. This is describing exactly what. Anything at the focus, the light reflects. And there's a parabolic reflector, as in your flashlight, your headlamps, those kinds of things. Or turn it around and it's your parabolic receiver, okay? And this is what I was telling you. I forgot they had it here. Ellipses. Here's a definition of an ellipse. Ellipse is a set of all points x, y, the sum of whose distances from two distinct fixed points is called the foci. The 2 points are called each point is a focus, so the two of them are foci, plural for focus, okay? And the fixed distance between the sum of the distances of those is equal. The sum of whose distance from the two distinct fixed points is constant. They've got all these other phrases in there. The sum is constant. D1 plus D2 is a constant. Okay? And it turns out, as you move around here, of course, the D1 gets shorter, D2 is getting longer, but it's a constant. Okay? When it's over here, your D1 and your D2, that's an easy way to figure out what that is. Distance of this plus the distance of that, or distance of this plus the distance of that. At the same time, the line through the focus intersects the ellipse at 2 points called the vertices. Okay? The line through the foci intersect the ellipse at 2 points. They're saying this line, there's a vertex, there's a vertex. Now, I call those the major vertices, but the major axis goes through those. The center of the vertex is the midpoint of that major axis. The minor axis is then the perpendicular line to the major axis that also intersects those. I kind of call these vertices as well. They don't call it that. I call these the minor vertices. Those are the major vertices, but they don't call it. They just call those the vertex and the other the minor axis. Okay. Here's the standard equation of an ellipse. Okay. Now, I'm not going to go into it in great detail, but this is why I like to give you the second definition of the circle, if you remember that. X minus h squared over a squared plus y minus k squared over b squared is equal to 1. If the a and the b are the same, that's the circle. Okay? If they're different, it's an ellipse. Both of those have pluses there. Okay. Now you could have written that as x minus h over, I'm sorry. This is the major axis being horizontal, and this is the major axis being vertical. Okay. In other words, A is always greater than B. I don't know. Oh, there it is. Where A is greater than B. Whichever one is the larger number down here, that's going to be your major axis. A is larger than it's the horizontal axis. A is larger here, so it's the vertical axis. It's your major axis. The foci lie on the major axis, C units from the center, okay, with C squared equal A squared minus B squared. Okay. That's a little more detail than I think you'll need, but that's why I like the form for a circle. It looks more like the form for an ellipse. Now, I'm not going to go back and redo the form for a parabola, but you'll see it does. You can visualize the definition of ellipse by imagining two thumbtacks placed at the foci and then doing this. Do any of you remember a toy called a spirograph or something like that? It had a series of gears and you could put different things in it and take a pencil and move around the gears, and it formed a variety of shapes and stuff. This is basically doing a real simple one, that focus with the tacks at the foci. Okay. And how do you find the center of the vertices and focus of a foci of an ellipse? Complete a square. Why not? Get your x terms together, your y terms together, complete both squares, divide by your constant at the end, and you got it done. Okay, I'm not going into great detail. Which of these would be the major axis, x or y? One with the biggest number down here. What is the a here? This is a squared. That would be 4. The b here would be 2. Yeah, that's how they look. Okay, center, of course, would be at 1, -2. Remember, this is always the opposite sign here. X minus 1, the center would be at 1. Y plus 2, the center would be at y is equal to -2. Okay. So there's your H, there's your K, That's what I just told you, 1 and -2. The A is 4, the B is 2. Okay? And C would be square root of A squared minus 2. So you can go back and do this if you want. That minor x is vertical. The major x is vertical. Now, the reflective property of an ellipse, at P, any point on the ellipse, the tangent line to the ellipse at a point P makes equal angles with the lines through P and the foci. Now, one of the reasons astronomers had difficulty detecting orbits of planets and ellipses, that they are ellipses, are the fact that the foci of the planetary orbits are relatively close to the center of the sun, making the orbits nearly circular. But they're never both at the center. They're close. Okay? To measure the ovalness of an ellipse, you use the term eccentricity. And here's the definition for that. Eccentricity is the ratio of C to A, where C is the square root of A squared minus B squared, and A is just A. Okay? That's how far out of being a circle it is. Okay. By the way, I'll say this. Most of your planets, the eccentricity is awfully close to 1. Okay? Because they're very close to each other. Pluto, way different from 1. That's one reason it's no longer considered a planet. It's a minor planet. Okay? Because its eccentricity was way, way too great. That's one of the reasons, not the only reason. For an ellipse that is nearly circular, the foci are close to the center. The ratio C to A is close to 0. For an elongated ellipse, the foci are very close to the vertices, and the ratio is very close to 1. Okay. And here are the 8 major planets, the 8 planets, okay? And you notice all Mercury, one reason it's so close to the sun that it's, even though it seems to be a near circular orbit, it's so close that it's that. But the others are very close. Venus, closest to being circular, okay? Mars, the next to Mercury, the furthest from being circular. And then the others are all within. Earth is pretty close. Neptune being so awfully far away has a very small eccentricity. But Earth being so close, well, Venus, that's just amazing. It's that circular, close to being circular. And Earth is next closest after Venus. Okay. After Neptune, Neptune's so far away, that contributes to its eccentricity being closer to 0. And then the areas of ellipse. All stuff, if you're interested in it, go for it. If you're into astronomy, you'll find it interesting. It's not so simple, however, to find circumference of an ellipse, so we're probably not even going to try that. Let's just quickly go through hyperbola. I just want you to see these major definitions, okay? This is the hyperbola set of all points for the absolute value of the difference between of 2 distinct fixed points called the foci is constant, okay? The absolute value of the difference, not the sum, the difference, okay? So in this case, your foci are inside the curves of the hyperbole, and the difference between the values are constant, okay? If D2 is always greater than D1, then you've got this limb of a hyperbola. If the D1 is greater than D2, then you've got this one. So the absolute value is constant, and that's why they're exact mirror images of each other. Center, of course, is the point exactly in between the two foci, which is also in between the 2 vertices. The 2 vertices are the point, just like you define it for an ellipse through the that are collinear with the foci. Okay, those are called the vertices. And that's probably one reason they don't call it for an ellipse a major and minus like I do, because this doesn't have one. Now, the line segment connecting the vertices is the transverse axis, and the midpoint of the transverse axis is center, and one distinguishing feature of the hyperbola is that its graph has two separate branches, not connected. They kind of look like individual parabolae, but they're not parabolae. Okay. Here's a standard form for a hyperbola. Look at this, equal 1. Okay, that's the joint. Difference here for hyperbola is a minus sign in between. If the hyperbola, the transverse axis is horizontal, the x is the positive 1, y is the negative 1. Okay? If it's the vertical, then the y is positive and the x is on the negative side. Okay? The vertices are A units from the center, and the foci are C units from the center. Okay? And then this is the relationship between B's and C's. Okay? But that's what I want you to see. With a circle, plus sign, A and B are the same. For an ellipse, plus sign, A and B are different. For a hyperbola, minus sign and A and B could be the same or different. It doesn't matter. Okay? Then there's the other things, the asymptotes. See, a parabola doesn't have an asymptote. A hyperbola does. Okay? There's some line that is approaching. It gets closer and closer but never crosses. A parabola keeps spreading. Okay? Then they also have a thing called the conjugate axis. We're not concerned with that here. I wanted you to know those formulas. There's the formulas for the asymptotes of a hyperbola. If you ever need them, there they are. Okay. I'm not going to test you on them, of course. Okay. And here's other features of the hyperbola. How do you go about sketching? Guess what? Get it into standard form. Okay. And then you can pick up what your A and your B and your calculate what C is. Okay. You're not going to be required to do the eccentricity of a hyperbola, just like it was for an ellipse, C over A. Okay? This is one with a very large eccentricity. There's one closer to 1. See, for ellipses, they're either 0 or 1, between 0 and 1. For hyperbole, they're 1 or very close to 1 or extremely large. Okay, that's all we needed in that. I didn't know I wrote anything on it. So Les, please move on. This you are responsible for, and I'm sorry I've taken so much time, but I wanted you to be exposed to that stuff. So let's move on. I didn't even turn pages of the book. And by the way, I should have turned pages of the book because there are some more potential paper topics. One was Hypatia is a person you could write on. Pretty amazing kind of person there. There's some other people mentioned here. Apollonius and others. Alexandrian. I'm sorry. You can read that. I don't have my glasses on. I'm having trouble focusing on it. Nikolai Copernicus, okay? Known more as an astronomer, but guess what? Everything he did was based on conic sections, okay? He said the planets travel in elliptical orbits, okay? And then there's a Caroline Herschel, another woman here. First woman to be credited with detecting a new comet was an English astronomer, Caroline Herschel, and during her life she discovered a total of 8 new comets. Believed she was the wife of an astronomer, and she outdid him big time. He had the job, she did the work. Okay, not too surprising. All right, let's move on to 8.2. Okay, let's go from current slide. Chapter 10, we've already done everything we're going to do with conics and more. Parametric equations, polar coordinates. This is plane curves and parametric equations. Okay. Sketch the graph. Objectives here. Sketch the graph of a curve given by a set of parametric equations. Eliminate the parameter in a set of parametric equations if possible. Most of the time it is, but there will be occasions where it's not. We'll find a set of parametric equations to represent a curve. Here we sketch the curve based on the parametric equation. Here we'll find a set of parametric equations to represent a curve. Understand two classic calculus problems, tautochrome and histochrome. Basically, pronouncing them is the hard part. Okay, so anyway, there's that. Now, again, we're talking about a plane. That's why everything is talked about. You're dealing with two equations. Okay, they don't quite say it, but you usually are. When they say a set of equations, it's usually a set of two equations, because you're talking about a plane. Consider the path followed by an object that is propelled into the air at an angle of 45 degrees. Okay? For the initial velocity of the object is 48 feet per second. The object travels in a parabolic path given by the rectangular equation, this. You might say, where did that come from? Okay? Very legitimate question. Okay? They just gave it to you. They say it is there. Here's the rectangular equation, something projectile object propelled into the air at an angle of 45 degrees. Okay? Now, this equation, I can't even begin to say, here's how you do it. However, the parametric equations are pretty straightforward. Okay? Because of this. If it's at 45 degrees and the initial velocity is 45 feet per second, that means that initial velocity, which would be the tangent line to this curve right here, is at 45 degrees. So the initial velocity has one component in the x direction, another in the y direction. And those two components are equal because it's 45 degrees. One's the cosine, one's the sine. 45 degrees, which is root 2 over 2. So if the hypotenuse then of that thing is 48, and root 2 over 2, that's where, well, I'm using physics more than the, well, no. It's on the next slide. Okay. Parametric equation, x is equal to, and by the way, the x component of that velocity never changes. Because you know why, right? There is no force acting that would change that. The only force acting on it when it's projectile, propelled, is gravity pulling down. There is no, so the velocity in the horizontal direction is constant, and it is 24 root 2 times the time that's the x is just that expression. So linear expression, 24 root 2. And that comes from, let me see if they can give it to you. No, I don't think they do. Okay. Let me show you. Let me get my pen set up. All right. No, it didn't take. Why is that not doing? Okay. Here's your initial velocity here. It's a 45 degree angle. So your x component is, this is 48 this way. Well, the cosine of this angle here, this is 45 degrees, cosine, the x component is 48 times the cosine of 45 degrees. And please tell me you know what the cosine of 45 is, right? Is root 2 over 2. 2 will go into 48 24 times, so x is equal to 24 root 2 times t. Okay, that just means that x is always the same. T is your parameter here, okay? Now, the initial y component is also, this is now the sine. The y component is equal to 48 times the sine of 45 degrees, which is exactly the same. That is 24 root 2 t. That's only when when t is equal to 0. Okay? So that's the initial. Well, there's your initial velocity right there. Is that. But your y is being subtracted by, and this is in feet per second, so the acceleration due to gravity minus 32 feet per second squared, 1/2 of that is 16, minus 16. So this is coming straight from physics, okay? Now, they just gave them to you. They said, this is what they are, okay? It's true, but that's where they came from, okay? Now, this is called curvilinear motion, 2 variables for position, 1 variable for time. Time is the independent variable. X and Y both depend on time. So they're both dependent variables. Okay. Now, how in the world do we get this? Okay. Well, let's solve that first one for t. Okay. And that would be, let me write this again. X is equal to 24 root 2 t. Solve for t, you would divide both sides by 24 root 2. So these go away, and rather than doing that, I'm going to multiply by root 2 over root 2, and that will make this 2, which makes that back to 48. So this will be root 2 over 48 is equal to t, because I didn't like having the square root of 2 in the denominator. Okay? Now, plug this value in for the t here. So y is equal to minus 16 times t squared. Well, root 2 squared would be 2, and 48 squared would be 48 squared. Okay, I'm not going to figure out what that is. Okay? Plus 24 root 2 times root 2 over 48, which seems like we're running in circles here. Okay? Well, this root 2 times that root 2 would be 2, so this is plus 1. Okay? That just equals 1. So, now, I know that 16 will go into 48 3 times, right? Okay, so this would be 3 times 48, because it was 48 squared. I divided the 16 into one of the 48s and left the other. And then this gives you 3 times 48 is 144. Divided by 2 is 72. So you get minus x squared over 72 plus x. Okay? Oh, I'm sorry. I left off my x here. Yuck. This has an x, and everywhere there's an x. Okay. And that's how, I'm sorry, I forgot to put my x in. But that's where this equation comes from. I wish they had shown it to you. They just said, oh, behold this. And then this can be done like this without ever telling you why. Okay? Well, that's why. Sorry. I'm in too big of a rush. Okay. So this is your xy equation for that curve. Here is your parametric equation for the curve. It's the same curve with one exception. This would just be this curve here with no error on it, because there's no error involved. This one, though, when you have a parameter t, when t is 0, this is obviously 0, and this will be 0 plus 0. That would be 0. So there's where you start. Here's where you end up. So you're going from here to there. So a parametric equation always has an arrow with it. Okay? The recto, what do they call that? Rectangular coordinates, they don't have the arrow. Okay? When you just have x's and y's. Okay. To determine this time, you introduce a third parameter t called a parameter. By writing both x and y as functions of t, you obtain the parametric equations. X is equal to 24 root 2t. Now, I told you how to get that. It's using your, basically your trig function. And then the y value you get from physics. Acceleration in feet per second squared would be 32, but it's 1/2 t squared. So that's where you get that. Now, you don't have to know physics to get it. They're just saying, here are the parametric equations that gave you the other equation. Okay. From this set of equations, you can determine that at time t equals 0, you're at 0, 0. Somewhere at time t equal 1, you're at the t peak up there, and then so on. And that's what they meant by t is equal to 1 is at the peak, the maximum displacement. Okay. By writing both the x and y as functions of t, you obtain the parametric equations, this. Okay. For this particular motion problem, x and y are continuous functions of t, and the resulting path is called a plane curve. Two equations, one parameter, is always going to give you something in a plane. Okay. So the definition of a plane curve, if f and g are continuous functions of t on some interval I, we didn't talk about what the interval was, and we'll go back and do that, where x is equal to f of t, y is equal to g of t, these are parametric equations, t is the parameter. The set of points x, y obtained as t varies over the time interval I is the graph of the parametric equations. Taken together, the parametric equations and the graph are called a plane curve, denoted by the capital C. Okay. For ours back there, the t was the interval I, it was from 0 to 2. Now, there wasn't any way of telling that, but that's what it was. If you had let t continue to increase past 2, then this is going to dominate, this is not. So basically, you have other stuff going on that wouldn't have made sense physically, because you've hit the ground then. Okay. So that's why I said t is the interval there is 0 to 2, the one that they showed. Okay. When sketching a curve represented by a set of parametric equations, you can plot the points on the xy plane. Each set of coordinates xy is determined from the value chosen from the parameter t. By plotting the resulting points in order of increasing values of t, the curve is traced out in a specific direction. That is called the orientation of the curve. Now, they're using a lot of blah, blah, blah words, but you notice what they're doing. You're given x is some function of t, y is some other function of t. What I suggest you do if you're plotting the graph, set up your t table, only it's a different t now. X, y. But x is a function of t, y is a function of t. Pick values for it. So you actually have 3. T, x, and y. Okay? This is your independent variable, t. Pick values here, calculate what x is based on this function, calculate what y is based on this function. This gives you your ordered pairs for your graph. The t is not part of the graph. The t just gives you the values. So set it up, only it's a 3 table, not a 2-column table, 3. T, x, and y. And let your t vary as however you want it to be. Calculate x from t, calculate y from t. Okay? When you get the points, this is what you plot on the graph. That gives you the curve C. All right, so let's do it. Sketch the curve described by the parametric. How much time have we have? Second?
We're out of time.
We're out of time right now. We'll start next time. Sorry we're not getting any more done than this. You are responsible for this, though. Okay? So we didn't get enough done for you to have many homework exercises. You can start looking at them, but we'll begin right there next time. And we'll get as far as we can in 10.2, and it's a fairly short section, so we'll move on into 10.3, which is another fairly short section. I don't know how far we'll get, but we'll get as far as we can. If we have time, we'll do polar coordinates. But frankly, I've just given you an example of polar coordinates right there when we did that problem, when you calculate your x and your y. So my guess, we're not going to get until 11 at all, as far as we can in 10. So your final exam will only be covering sections, was it 9.1 and 9.2, sequences and series, and then in 10, 10.2, and 10.3, if we get to 10.4, that'll be it. It'll be a fairly short final, unfortunately way too easy, but I need to get those papers and your first two tests in by Wednesday, if possible. I want to return all the tests to you on Wednesday. Oh, get any help from me now? Good deal, thank you. All right.